the year. Kind of starting with this unit. Not specifically today, but with this unit, kind of like every problem is going to have like factoring involved within it. So we're going to do a warm-up today with some quick, easy factoring ones. And then next time, when we have a factoring review day, we will get more into the like ones that are more difficult. But that's why that factoring review on Delta Math was so important for you guys to do before this unit, because we're not really going to spend a whole lot of time going over like this is how we factor again. You guys are lucky because you get the factoring review day. Green Day classes don't, because they lose it with the PSAT. So why are these questions the easy factoring questions?
Because they're simple, we can figure out all of them.
Okay, they're simple. We can figure it out. Then why are these easier than other factoring questions? Why is this one? Why are these ones easier? Why do you think so?
They all have a coefficient.
Do what?
They all have a coefficient.
Ooh, in front of what term?
The x.
The x squared. You're right. So why these ones are easier is, notice we, you notice that they don't have a coefficient. They do have a coefficient. What's our coefficient they all have though?
4.
Great. So when you're what we call a, which is your coefficient in front of x squared, when we're in standard form, which you'll see in a minute, when that is 1, we got our easy, quick factoring. And what our easy, quick factoring is you just think of two numbers, what multiplies to give you your last term, which is c, and adds to the middle term, which is b. So remember, adding to that middle term, multiplying to the last one. And remember, looking at the setup of your factors, you can always multiply or like FOIL to multiply back through to make sure that your factoring works. So let's hear from you guys in our front table near my desk. What were the factors for our first question?
2 and 3.
Right, and this is that it should be x plus 2 and x plus 3, because 2 times 3 multiplies to give us 6 and adds to 5. All right, let's hear from you guys in that back table near the flag. What about for our next factors?
Negative 5 and negative 1.
Great job. So x minus 1 and x minus 5. Those two multiply to 5 and add to negative 6. Let's hear from you guys in our front middle table. What are the factors for our next problem?
Positive negative 2.
Good job. X plus 5 and x minus 2. Multiply to give us a negative 10 and add to a positive 3. Remember, looking at your last term, if it is negative, notice one sign should be positive, one sign should be negative. That's the only way you multiply to a negative number. If your last term is positive, you're going to have the same sign, either both positive or both negative, depending on that middle value. And let's hear from you guys in the middle back. If we have x squared minus 9, what are those factors? What are you guys thinking about with our last one, if we have x squared minus 9? Do you have that middle x term? Do we see an x term in the middle? No, so that means that what's that coefficient from the x term if it's not there? 0. So think about what multiplies to give us negative 9 and adds to 0. Do you want to help them out, Yoda? Good job. So this is our difference of squares factoring, meaning difference means what operation? Subtraction, and both of these values are perfect squares. So when we have that, that's going to be kind of like your factoring form is going to look like the square root of your first term, and then plus minus in each of the factors, and then square root in the second. All right. Any other factoring questions, things wondering about before we get started with our quadratics day 1? All right, so what we're going to go over today is we're going to go over some topics, ideas once again from Unit 1, but all based on quadratics. So we're going to go over some graphs and transformations. We're also going to graph in vertex form. So here we have our parent function for a quadratic. How do I know that that is a quadratic?
It's a square.
Awesome. Numbers squared, your exponent of 2 means you're going to have a quadratic. And what does a quadratic graph look like? What shape?
A U.
Like a U. So we are not an, I know, oh so sad, we're not an absolute value world anymore with our graphs looking like these. So quadratics and absolute values have a lot of similar characteristics, but the shape is different, right? Imagine if you're writing in English, right? Writing the letter V is different than writing the letter U. So therefore graphing like a shape of a U is different than graphing a V. So it might kind of make that distinguish between your graphs. So with my parent function, whenever you're talking about graphing and creating graphs, go back to your foundation and your basics of inputs and outputs. So if I'm creating my input table, I'd have that maybe -2, -1, 0, 1, and 2. If these are my inputs, kind of think about those are those values like centered around my graph because I'm creating the parent function. Let's think about what are the outputs. That's what f of x means. So if I input -2 into my function, what would the output become? 4. What about if I input -1? What about if I input 0? What about if I input 1? And what about if I input 2? Great, so let's graph these points on our graph to see the characteristics and the shapes that we have going on. All right, so notice we have our U-shaped graph. Remember that U-shaped graph is called the parabola. For that U, it's no longer a V. So always go back to that foundation of those inputs and outputs to create those good points. What are some kind of characteristics or generalizations you're noticing about our quadratic? What do you see, Yalda?
All positive outputs.
Ooh, think about what Yalda just said. All positive outputs. What characteristic did she just describe?
Absolute value.
Oh, absolute value is similar to that in the sense of you have positive outputs, right? Because anytime you square a value, like if I square a negative, it's positive. If I square a positive, it's positive. But when Yalda said all positive outputs, what characteristic does that describe? Think about your characteristics from Unit 1. Y values, which is?
Range.
Yes. So thinking about all positive outputs, that's talking about our range here. What other characteristics are you noticing? No right or wrong answers, it's just kind of like what you see, what you notice. Okay, good. So Liam's describing the domain from -infinity to infinity. So basically, think about what a quadratic does. Can I input anything into a quadratic? Yeah, that's what we were just talking about. Domain, inputs. I can input, but can I get everything back out? No. So that's kind of like what connections between those two. So thinking about that domain and the range, right? All throughout our quadratics unit, you're always going to have that domain of -infinity to infinity, because no matter if my U looks like this, or maybe if my U is upside down, or if my U is shifted left, right, up, down, or maybe got wider or is more narrow, it's still going to be able to extend to the left forever and extend to the right forever for our domain for -infinity to infinity. Let's see one other idea. One other characteristic, and then we'll move on. What do you want to add on, Between?
Symmetrical.
Ooh, good word. It's symmetrical. So we have a new characteristic, new idea when we talk about quadratics, and it's going to talk about that idea of being symmetrical. How would you describe, where is this graph symmetrical about? What are you kind of seeing?
Over the Y.
The y-axis, so if I'm symmetrical about the y-axis, right here, this is our new characteristics, which we call our axis of symmetry. And thinking about what does that look like? That is a line. And what type of line is this axis of symmetry? A line that looks like this is a vertical line. So what would the equation of this vertical line be here? Okay, but what's that equation? That line is right on top of the y-axis. X equals y is a diagonal line like this. It would be x equals what?
0.
Yeah, x equals 0. That's your vertical line. So that's going to be a new idea for our axis of symmetry. So this is some good things we're already starting to develop and think about. I'm going to have you guys now kind of put some of those down for their characteristics. So here we have our parent function of f of x is x squared. And why don't you guys take a minute, and we've already talked about a couple of those ideas, right? Domain, range, that axis of symmetry. Fill in the rest, and then we'll go over them. Let's run through this to see what you guys were thinking. And we already had some ideas. Liam told us our domain was negative infinity to infinity. And then Yoba said that the range would be like all positive outputs. So what would that range be in interval notation if you're saying all positive outputs? So would it be Yoba?
Like continuous bracket, 0, infinity.
Awesome. Okay, then let's hear from you guys at back table near the door. Do we have an extrema? Awesome. We have an absolute minimum at 0, 0. Great job. And then let's come back around my table near my desk. Where are we increasing here? What do you guys see? Did we increase on this graph? Yeah, where did we increase?
0 to infinity.
Good job. We increased from 0 to infinity. And then what about you guys in that back table? Did we decrease? Good job. Negative infinity to 0. Then do we have any intercepts about you guys in that back middle table?
Only 0, 0.
Only 0, 0. And then we talked about it before. See what you guys remember in that front middle table. What was our axis of symmetry? Remember, it's going to be this line that you can cut through our graph. Do you remember what that equation was? What do you remember?
X equals 0.
Great job. So remember, it's an equation for a vertical line. So that's x equals 0.
What would be the slope of the graph?
Thinking ahead. We're going to get there. So just you wait. I'm going to keep you on your toes. So as x goes to negative infinity, so we're looking to the left side of our graph. Where are we going here? Yep, we're going up to positive infinity. And as x goes to positive infinity, where are we going? Good job. Infinity as well. Anybody have any other generalizations we want to make about quadratic graphs to add versus what we talked about on the last slide? Any other ideas you want to make any generalizations about other than domain, range, that axis of symmetry?
Exponential slope.
Ooh, nice idea. So Liam said there's an exponential slope. Thinking about our absolute value functions, you have that constant rate because those absolute values, kind of think about were kind of, you could define as a piecewise of like two different lines. So they have that constant rate like that slope idea. This does not have that constant rate. So we are not going to be able to just keep going up one over one, right? I can't keep doing that because that's not quite working out. So we're going to talk about like how to find what exactly would our A value be and kind of how to get to our next couple of good points. I will say though, if you look to the left and to the right and you see, noticing here's my vertex, if I look to the left one and to the right one, that can kind of give you a good estimate, and we'll prove algebraically what that A value would be. So if I went to the left and to the right one and up one, what are you going to predict the A value would be here? 1, right? That's like up 1 over 1. And then kind of noting here to get to the point after that, notice I'm going up 4 over 2. Kind of think about what does that mean? When my x is 2 away, what's 2 squared? 4. So think about I got 4 up. So that's why it was 1 for 1, meaning over 1, x is 1, 1 squared, up 1, over 2, 2 squared. So if you could imagine 3, 1, 2, 3 is going to be like 9 up. But we're going to still use that algebra, like inputs, outputs, because it's good foundation to just kind of help us really figure out what exactly those points are. So we have 3 different quadratic forms, and we're going to keep bringing this up kind of throughout class, throughout this unit. Today we're only focusing on vertex form. We did start off in standard form with our warm-up when we were factoring, and then notice to get to intercept form, what does it look like you're going to have to do? What does intercept form look like it's kind of made up of? What do you call those guys? Hints right there. They're factors, right? So your intercept form is kind of made up of your factors. Standard form, that ax squared plus bx plus c. Saw some of those in your warm-up. Vertex form is really what we're going to focus in on today. That's kind of only the one you want to jot down. Like I said, you're going to keep seeing those others throughout your slides, so you don't have to jot them down. You'll kind of keep seeing them class after class. So the vertex form is going to be set up nicely, and that's the easiest one to graph in because it's going to show us and tell us about our transformations. So looking at our vertex form, I want you guys to take a moment looking at that vertex form and predict kind of what transformations might be occurring here. Think about those transformations we've talked about before. Anybody want to take a guess on like any transformations that might be happening here? What do you think, Mithra?
I think like alternate the slope.
Oh, okay, great. But I'm not going to use the word slope, right? Because that's that constant rate. So what other words have we used before that like can kind of change it? Compression or stretch. Okay, good. So I have 3 scenarios. So if that A value is greater than 1, is that going to be a stretch or compress? Stretch. Good. And then what about if it's less than 1? What would that be? Compress. How else could that A value change? Anybody have any other predictions?
Negative.
Ooh, what would happen if it's negative?
It would reflect over the x-axis.
Good job. Great job of saying not only will it reflect, but over the x-axis. You guys, a few of you on your test were only saying reflect instead of over the x-axis. Remember, another transformation is reflecting over the y. So we want to make sure we distinguish between the two. All right, what other transformations do you guys predict might be happening? What do you see, Laura?
It moves to the left or right and for the H.
Yeah, good. Remember, inside your parentheses, just like we did back with Unit 1, inside those parentheses are going to kind of shift your x, moving along your x-axis, so left or right, just like Laura said. So if you see a minus h, what direction do you think that's going to shift your graph? Good. Same idea with that insider's lie. And then what about if you go plus h? Left. All right, what other transformations do you predict might happen?
Move up and down.
Ooh, up and down. How do you see that?
Good.
Good job. So if I have a plus k, what direction would that shift my graph?
Up.
What about if it's a minus instead? Good. So really similar to kind of that like first unit with those parentheses, kind of knowing inside the parentheses, left or right, that number outside, up or down. It's still your A value, like from our absolute value is going to make that stretch, compress, or reflect. So let's look at this example. So write the equation for the quadratic with the following transformations, reflecting over the x-axis, vertical compression by 1/3, right 4, up 5. Why don't you guys take a minute to do that, and then we'll see what you came up with. All right, let's see what you guys were thinking. Who wants to try? What do we think the A value is here? What do you think, Yelda? Good job. How do you know it's negative 1/3? Amazing. Anybody have any thoughts? What should go in the parentheses with X? What was that? Good. How do you know -4? What told you to just go -4? Awesome. Right 4. What about outside here? What should we do? What was that, Sarah? Good job. How do you know +5? Awesome. It tells us up 5. All right, you guys. Let's keep moving on. We're going to write the equation now given the graph in our vertex form. So I'll kind of put up here the outline of your vertex form. While I'm doing that, what I want you guys to do is look at the graph and jot down the transformations you're seeing. So write down those transformations, then we'll see what you guys got. Good morning, Vita.
Good morning.
All right, guys, here's our equation in vertex form. Looking at your graph, what are some transformations you saw? What are some transformations you see here? What do you see, Evan?
Down 5.
Oh, we see down 5. So if I went down 5, how is that going to affect my equation?
-5 and 10.
Great job. What else do you guys see? What do you see, Vivian?
Vertical stretch of 2.
Ooh, so Vivian's seeing that vertical stretch of 2. How'd you notice that?
Because it's like at the bottom and moves over 1 out 2.
Good. So Vivian's saying from my vertex, I went up 2 over 1 in both directions. Remember how I said you can kind of use that as a prediction, but we're going to solve algebraically to confirm. So we're going to keep that in mind, and we're going to confirm algebraically. So for right now, I'm going to write this A, just to kind of keep that in mind of like, okay, I'm going to come back. I want to confirm algebraically. So I'm still missing this one piece here. What's that inside with my parentheses? What should we have? What do you see, Laura?
+4.
How do you know +4?
Because they're going to the left 4 pieces.
Great job. So this is kind of my template, my outline. Vivian was saying, okay, I think that this is a vertical stretch of 2, but I will let you guys know when it is fractions, it's a lot more difficult to distinguish and notice your stretch or your compression. So we're going to go over how to find that piece algebraically. So if you ever don't quite know, you can use this as a tool to help you, and we can kind of, we can predict right now that it's 2, but we're going to confirm algebraically. So how can we confirm algebraically? thinking about right now, I really have 3 variables. What could I use from my graph? So therefore, I only have the variable a to solve for.
You go off and use this. Has overrun.
Oh, okay. So I think you're thinking about something different. What do you think about Ruby? Oh, I could plug in maybe a Ruby saying like a point, right? So what would happen if I plugged in the vertex here? What's the x value? -4. So if I plugged in -4 here, -4 plus 4 is going to give us 0. 0 squared, 0. 0 times a. Is that going to help us find a? No. So Ruby was on it in the sense of plugging in a point, but we just can't plug in the vertex because that's going to zero out a and not help us find a. So let's pick one of these other points to help us. So what's another good point we could use? What do you guys see? What's another good point? All right, good. We have the point -5, -3. So thinking about plugging those values in, f of x we know is the same thing as what? Y. And what's our y value? -3. Good. So we have a times instead of x. We'll use our x value here of -5. And now we're going to solve for a. So let's just do some order of operations to help us get there. -5 plus 4 I know is going to be -1. And what's -1 squared? 1. So 1 times a is just a. So now I have the equation -3 equals a minus 5. So what do I know a is going to equal? 2. And is that what Vivian predicted the stretch was? Yeah, good. So that's how we can confirm algebraically. Using that prediction is a good way to kind of, okay, like I'm going to predict it's 2, but let's confirm algebraically just to be sure in case I'm dealing with some fractions. So there's our equation in vertex form. And if you want to check to make sure your equation's right, remember you can always plug in other good points, right? Like if I plug in like -2, what do I expect the output to be? 3. Think about just ideas like that. All right, you guys, any other questions here? I will say that finding a right here is probably the trickiest thing we're going to do today. So if you feel good about that, it's kind of good track. All right, so looking at our next example, we're going to graph this given function. We have -1/2 times x minus 3 squared plus 6. So why don't you guys take a minute, jot down that equation, and before we graph it, why don't you identify those transformations that you're seeing here to help us with that graphing. All right, guys, so what are the transformations you see from our equation here? What are some transformations you guys see? Good job. We reflect over x. We have this negative out in front. What else do you guys see?
Right 3.
Good job. We go right 3. Where? What else do you see? What do you see, Morgan?
Up 6.
Up 6. And anything else? Is that it? Did we get all the transformations? What do you see, Laura? Good job. Compressed by 1/2. So back with our absolute value graphs. When we were graphing our absolute value functions, what was the first point we always put on our graph? The vertex, we're going to do the same idea here. Where is our vertex located? 3, 6. How'd you get that, Ruby? Awesome. I start at 0, 0. We go right 3, up 6. Now, when we had our absolute value, we then use that a value like slope. But here, my a value is not consistent in the sense of I'm not going to always be going down 1 over 2, down 1 over 2. So what we're going to do is we're going to go back to our foundations, the basics, and make some inputs and outputs to help us kind of get those good points. So I already have an input of 3, 6. Think about that's my vertex, kind of, and I'm thinking about my graph being symmetrical. So if I'm thinking about getting 5 good points, I want to get 2 to the left and then 2 to the right of my vertex. So thinking about that, what would be like a good point I would want to input to help me find like a good output? Would be like a good point to input into the function to find a good output. Okay, so I could input 0. I can always input 0, right? If I input 0, that is going to give me what value on my graph? Think about what characteristic on my graph will I always find when I input 0?
A y-intercept.
The y-intercept. So let's input 0 and find out what's the output. So if I input 0, 0 minus 3 is going to give us negative 3. What's negative 3 squared is 9. 9 times negative a half is negative 9 over 2. So I'm going to have negative 9 over 2 plus 6. And what is that going to become? So remember 6 over 2, to add them together, we need a common denominator, right? So that's just 12 over 2.
3 halves.
Yeah, 3 over 2, which I know is 1.5. So right here. All right, what's another good point? That one gave me like not quite a good output, right? What could I input that I would have like a nice whole number output? What do you think, Yoda? All right, let's go with, I heard you say 5. Let's go with 5. And you also said 1. So if I input 5, think about 5 minus 3. I know 2. 2 squared is going to be 4. 4 times negative a half is going to be negative 2. What's negative 2 plus 6? Negative 2 plus 6 is 4. So I'm going to have to point 5, 4. Which also means, kind of think about, if I think about my good input of 1 here, I can probably predict 1 to be right there. Sorry, the 1 to have an output of 4 because that graph is symmetrical. But if I wanted to just double check, right, if I input 1, I'll have negative 2 squared back to 4, 4 times negative a half, negative 2 plus 6 still gives me that output of 4. So I'm like, yep, that was for sure right there. So I probably want to just get like maybe like 1 more other good point on my graph. I want to have like 5 good points at least. What's maybe 1 more good point? Think about I want to have another one to the right of our vertex.
6.
Okay, so if you input 6, so 6 minus 3 is going to give us 3. 3 squared, we know is 9, times negative a half, so I'm back up to here, so that's going to also give me 3 over 2, which is 1.5. We're going to go over later on about how to find those x-intercepts algebraically, but we always know for sure how to find those y-intercepts by doing that same process. That means our input is always 0. So you should have 5 good points or more on your graph. So think about vertex for sure, kind of think about your hand, vertex in the middle, and then 2 on the left and on the right. What other questions do you guys have about graphing? Any other questions? Okay, so what we're doing next is you see the 10 problems posted around the room in yellow paper. We're going to work on those 10 problems. You will probably finish before class is over. And if you do finish before class is over, check your work with the neighbors, see if they're getting the same things as you. You can hop on Delt's Mac to work on any of those reviews if you need to. You're showing your work on the paper that I'm passing out. 1 through 6 are on the front, and then 7 through 10 are on the back. So on the back, there's like grids for you to graph 4, 9, and 10, and then your characteristics outlined for 7 and 8. Let me know if you have any questions while you're working. Turn this in by the end of class, and if you do need more time to finish it before next class, if you go to our class slides for the day and the speaker notes, you'll find the problems linked there. What other questions do you guys have about it before I pass it out? Alrighty.